Hello, this is Stuart from Biocinematics. Welcome to another tutorial about molecules and Maya. So this is a render I created recently of a molecule that is a eukaryotic translation initiation factor. So what that means is basically it binds to the start of mRNA, messenger RNA here. So this is the 5' cap of messenger RNA, and it helps get the ribosome and other protein factors all connected together so that translation can begin. This was the February molecule of the month on the Protein Databank website. So Protein Databank website features different molecule each month, and this one, February, was the initiation factor, eIF4E. So on this illustration, I used the Molecular Maya modeling kit, which is a very handy add-on to Molecular Maya. And I thought I'd go over a little bit how the modeling kit works and how I used it on this illustration. So this isn't a comprehensive course on the modeling toolkit, just some of the subset of features that it has to kind of get you started if you're interested in looking at what that modeling kit can do. So Molecular Maya has the basic PDB import functionality and some other related things, and then there's a number of other kits that are available. The Molecular Maya base tool is free, and you can get it on here, clarifai.com/tool/mmaya, and that's free. But if you're interested in getting some of the additional kits that allow you to do other things, those are additional add-ons that you can buy. And I think this modeling kit is pretty cool, so that's what I'm going to explore today. If you haven't used Molecular Maya at all and you're wanting to know how that works, how to get going with that, I do have a video tutorial that you can view that should cover all of the basics of Molecular Maya, getting PDB data into Maya. And after that tutorial, you should be able to follow along pretty decently with the stuff that I'm going to cover today. Okay, so let's get started by doing a little bit of research on this particular molecule that we want to illustrate. That might be a little bit tedious or even boring for some people, but frankly that's just part and parcel of the process of making molecular illustrations, and hopefully I'll be able to share a few interesting helpful tips and ideas for looking at these kind of structures and really trying to understand what kind of data we need to import and make use of. The protein entry that we're going to be working with is 1EJ1, and I'm going to totally get that confused with eIF4E. We're going to jump over to here, and I'll try to keep it straight. So this is the entry for no, I can't do it. Forget it. You can see it on the screen. And basically what we're going to look at is what's contained within this PDB file, and if there's any sort of problems or issues that we need to tackle. We've got two chains that are the eukaryotic translation factor 4E, and we only need one of those. This is a monomeric protein, and I can tell that because I went into the literature and I pulled up the PDF and I searched for monomer, and we demonstrated that it was monomeric. And I also searched for dimer and nothing came up. So that's one way to tell. So the other thing to take note of here is when you look at the asymmetric unit, there's two copies of it, but that's just how it was crystallized. That's not how it appears in nature. And if you look at the biological assembly, you can see that it's just sitting on its own with a small molecule. So let's take a look at that. So we're going to be choosing either chain A or chain B to work with. And we also have a ligand. So this ligand is 7N-methyl, basically that's the 5' GTP, or GDP actually. It's a diphosphate, as you can see here. So we got two phosphates, and this is guanosine. So actually, in order to sort of visualize what we're looking at, we're actually just going to bring it into Maya. Okay, so we're going to a few import settings, and I think I covered these in the other tutorial in the introduction to Molecular Maya, but just to reiterate here, we do have some import options. And in this case, I do want definitely bonds and backbone. It's helpful to show the c-terminus labels. And we do also want the het atoms. So het atoms, those referred to atoms that are a cofactor, some other molecule, basically anything that's not part of the main protein chains. Het atoms are basically what's going to allow us to bring in that GDP ligand. So if we've got those checked, then we're going to go over to the download tab and we're going to type in, and I've already forgotten what it is. Why don't we just copy and paste it to avoid mistakes? Yeah, we'll check import post download. Okay, so here we go. So a couple things just to clean up the view here. Basically, I'm going to turn off atoms for the chains. So I've selected chain A and chain B and turned off the atoms because I'm just more interested in the backbones for those. So I'm going to turn on the backbone biz. So we've got chain A and chain B, and both of those are bound to this GDB. So let's go back to the PDB website and see if these chains include all of the data that we need. Okay, so one thing I like to do when I'm looking at the available information that we have on the PDB website is to look at the full protein view for a given protein. So in this case, eIF4E, and this is in the mouse. So it's a mouse protein, mus musculus, and we can, if we expand with this plus icon here, we can see that there's a whole bunch of entries corresponding to different PDB entries that represent this same molecule. 1EJ1, that's the one that we imported. That's the B chain, and then somewhere else down here, we've got the A chain. So what's the difference between these two? Basically, it looks like we have some of the entries that have the biggest coverage, which is what you're looking for. You want a lot of coverage here. If there's some that are down here at the bottom that don't have as much coverage. Blue bars represent the atomic coordinates that have been listed in the entry. So I'm going to minimize this again and just look at B and A. And I can tell immediately that B has a little bit more coverage than A. So let's see if that's reflected in Molecular Maya. So if I select the protein here and just go to protein or chain B, it looks like, yeah, so we can see these tags, enter, that's the N-terminus, and it looked like there was more information on the N-terminus of the B chain, and it looks like that's what we're seeing here, this extra little thing sticking out. So even though the B chain is longer and has more information, does it have all the information? Is it the full-length protein? So at this top of this protein feature view, you can see a few entries here that are under a category called UniProt KB. So this is the UniProt database. It's pulling information about what should the sequence be, what should all of the information be. So if we jump over to the UniProt website, we can kind of see the full length of the sequence that we're looking for. And we can do that by just clicking on this UniProt button here. And we can jump over to here to the UniProt website, this database entry for the same thing here. And I like to look at this sequence section here. So we can see the actual sequence of amino acids listed here. And this is the full length of the protein. Now, interestingly, so all proteins, at least generally speaking, they start with a methionine residue. That's the start codon. And we can see here that this little blue icon, if we click on that, we can see that that initiator methionine is removed in the functional protein. So, okay, so we can ignore that one. That's fine. But what about the rest of the stuff? Well, let's look back at our E1EJ1 entries. So chain B starts here at, and if we hover over it, I think there's a bit of a bug on the website. Maybe it's just me. Maybe this is how it is for everybody. But there's this black pop-up that pops up here, but it's way far away from a mouse pointer. So just take a look at that thing. So we can see that it starts at sequence position 28 and runs through all the way to sequence 217, whereas in the A chain, or actually there's no coordinates for residues 27 to 34, and it actually starts over at 36. So what does that correspond to? So sequence B starts with 28, which is this residue here. Chain A starts at 36, which is somewhere this residue over here. To get even deeper into this, now this is like super deep, we can look at the actual text file that is the PDB data that actually Molecular Maya is using, and kind of verify some of this information, which isn't necessary in every case, but it's just to kind of help understand what's going on and to kind of have a sanity check and make sure that things make sense and they are in alignment with what we're expecting. So if we jump down to line 355, we can actually see the sequence that's recorded in this PDB entry. So for the A chain here and the B chain here, actually from residue 28 to 217 is recorded in both of these, even though in chain A we're missing a few of the residues. And that's exactly what's being shown here in this pop-up here, where it says the coordinates haven't been determined for region 27 to 34, but the sequence is recorded in the records. But we can see the valine, alanine, asparagine, proline. That corresponds to valine, alanine, asparagine, proline. So that's where that sequence is starting. Okay, so all of that leads us to confirm that we're missing some information here. What's going on? What happened to this stuff? Well, if we look at another line here in this calculated disorder region, there's this red section. So red means a disordered part of the protein, blue is ordered. So that means that the structure is well defined. It's not flipping and flopping around. Okay, so we do have this very flexible region. So I went into the literature to see if something is said about this, and in fact, in the paper that was published with the PDB entry, we can see here the first 27 amino acids were omitted. In one half, residues 28 are not visible and are almost certainly disordered. Okay, so that's the disordered tail. Given the results, we suggest that the first 35 amino acids are disordered in the absence of other proteins. So in the other half of the asymmetric unit, they're talking about chain B here, residues 28 to 35 are stabilized by lattice packing interactions that are probably unique to this particular crystalline state of truncated blah, 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 blah. So what does that mean? In chain A, we were missing the whole flexible tail. In chain B, we're missing most of the flexible tail, but we do have part of that was stabilized by its local interactions with other things that are going on here. So this specific structure is kind of an artifact of the crystallization process. So that's interesting to know. So if we're going to choose one of these, which one is better? Well, in the end, it probably doesn't matter too much. So I'm going to go with chain B, but I think the important take-home point is that we're missing a good chunk of this flexible tail from this protein. So how are we going to get that? We still need residues 2 through 27. How are we going to get that? The answer is the Molecular Maya modeling kit. So if you made it this far, congratulations. Now we're diving into the actual functionality of the Molecular Maya tools. Okay, so before I get started, I'm just going to go into this structure and hide chain A and the labels and this guy here. I'm going to turn off the atomic viz and the NC labels. And in fact, I'm going to hide the NC labels on this GDP because they don't mean anything. That doesn't really make sense to have NC labels because there's no N and C terminus on a small molecule. Okay. So this is what our starting point is. So we need to extend this into a flexible tail. How do we do that? All right, so this modeling kit has some pretty nice features that allow us to do that. Basically, the modeling kit in part allows us to synthesize new peptides, and that's what we want to do here. We're going to synthesize the peptide that forms this part of the structure. So we can build from a residue count, just throw down random bunch of amino acids, but we do know the structure, or we do know the sequence rather. So we are going to build from a specific sequence. And basically we can just grab the sequence right from the UniProt website. So this is the sequence. We're going all the way up to residue and including residue 27. I'm going to ignore the methionine. So I'm going to copy that. And if you paste that right in, you'll see a couple things. The spaces were included and the text is black. So I'm going to paste it into Notepad, delete the spaces, and then copy that and paste it in here. And now we have our sequence here. Now, where do we want to synthesize it? We could synthesize it from an existing PDB chain, so we could choose chain B. But the problem with that is that it's going to synthesize it starting from the C-terminus. And we actually want it connected to the N-terminus, and there doesn't seem to be a way to specify that exactly. So I'm just going to set it at the origin, and we'll see later how we can connect it to the N-terminus here. So chain root and the secondary structure, we've got a couple of options. We could do an alpha helix, beta strand. We could do something a little bit more specialized, a custom. Because this is a disordered part of the protein, I'm just going to do none, and we can deal with the secondary structure, other aspects of it being flexible later on. Add anchors, we'll leave that checked, and we're just going to do build. Okay, so what Molecular Maya is doing is it's putting down some particles and it's simulating them. So you'll notice that our timeline got, you probably can't see it. Okay, there we go. So now you should see the timeline. basically it's simulated for a while these atoms, and so it's created this peptide chain just in a linear fashion right now, but it's already done some simulations so that the atoms, the bond angles, all of that is in a semi-favorable conformation. You can see up here we have this little element of the HUD that says peptide state great, so that means that there's not a whole bunch of steric forces and other things that are making this unfavorable or energetically bad. Now you might notice that we've been dropped into a new part of the molecular MI interface. So I'm going to go over some of this stuff, and if you lose it and you're back here and you want to know how to get back into where we were, you just need to open up the modeling peptide group and select your modeler chain 1. That's the molecule, the peptide that's been created. So you can see it's a completely separate thing than the PDB mol structs. So this is kind of a separate part. It's a separate module, it's a separate process, separate kind of data, and it's treated separately. Okay, very quickly let's look at the display options. So we can hide and show it. We can display the atoms as points or as spheres. And the labels, we could actually show the residue name, which is kind of cool. So we can go in here, and at the C-terminus we've got alanine, threonine, valine, glutamate, proline, glutamate, threonine, and that corresponds to these here. So we know that it's functioned correctly, which is cool. We can change how the bond is displayed, whether viewport lines, viewport cylinders, or actual geometry. I think just to keep things simulating quickly, viewport lines is fine. Okay, connections. So this is where we can actually connect up the the C-terminus of this peptide with the N-terminus of our existing chain. So we're going to select an existing chain to connect the modeling peptide to. We're going to select chain B. Obviously, that's the one we're working on. And the modeling peptide, we're going to connect the C-terminus of the modeling peptide to chain B. And it'll automatically know that you have to connect a C-terminus to an N-terminus. That's just how peptides form. Now the chain properties, so this is going to be deciding how we treat the existing chain. We can either ghost it, which means it's just going to basically be static. We could turn it into something of a collider and have this modeling peptide collide with the chain here. Or we can actually simulate the chain itself. So it's going to act as a collider, and it's going to drift and diffuse a little bit and react with the peptide. Now the problem here, I mean, there's a couple issues, but one problem is our peptide is just going straight through the chain. We could move the chain away, but I think there's no real reason that we need to move the original chain because it's not going to be interacting with it. It's just going to be floating off at this tail end. So in this situation, there's not really much point to having a collider or dynamics on the chain itself, but feel free to experiment with that. Okay, so we'll do connect to the selected chain. And now we have a few more options here. And we can turn on show links, and you can see that, there's a lot of stretch there. So what I'm going to do is I'm going to hit play pause in this interactive playback, and you can see it tries to resolve that stretch by bringing this terminus, or basically the termini, together. And that's pretty cool. So you can see I've got this interactive playback, and that's better than doing just hitting play on the timeline because the dynamics will play properly, and we also can still select things and work with things even as it's playing. So we'll see that a little bit later when we look at the handles. So I'm going to pause and rewind, and you can see it jumps back to the beginning. So if I hit play again and I increase the strength here, you can see that that's really going to increase how tightly those two termini are connected together. Okay, let's look at the handles tab here. So the handles allow us to work with the rest of the peptide. We want to create basically we want to bring this side around so it's a little sticking out a little bit more this way, or we can basically want to pose it. So we can create a handle at the beginning here, looking at residue 0. And if we're not sure which one that is, we can click focus, and it's going to zoom right in on residue 0. And I think that's fine. So I'm going to click create, and we get a little warning. We're going to say creating a handle requires rewinding the simulation. So the current state will be lost unless it's saved as a pose. We'll deal with poses a little bit later. So I'm just going to hit cancel, and I'm going to rewind, and I'm going to hit create again. And because we've rewound back to frame 1, this handle is now created. All right. So now I can hit play. And in addition to this part being drawn to that, if I start moving this handle around, we can see that this end is being drawn to this handle, which is pretty cool. So if I increase the strength of that, I can get something that reacts a little bit more quickly and more directly. And maybe I'll want to bring that around here, depending on the composition of my illustration or how I want this to behave. I can kind of start looking at posing this flexible tail. Okay, so I'm going to skip over dynamics for a second. I'm going to jump to structure because this is where we can talk about poses. There's two subtabs here, poses and export. So we'll look at the poses tab first. So this is how we can save this information, because right now if we hit rewind, it's going to jump back to that initial linear pose, which is not what we want, and that's stored in the initial pose. So what we can do is click new pose, and we get something called pose 1. I could just call this temp A, something like that for the time being, or even pose A if I'm kind of satisfied with how this is looking. And then we can load these poses and also rewind to the beginning of our simulation again. So for example, if I want to keep this pose and get back to the beginning to add more handles, for example, I can do load pose and rewind. And you can see that this structure hasn't changed, but we're back at frame 1. Similarly, we could do initial pose, load pose, and rewind, and now we're back to our initial linear thing. But we still have this data here. We've saved that as a pose, so that's cool. Okay, so now we're back at frame 1 again. So I'd like to add another handle to kind of deal with some of this middle part of this peptide. So I'm going to go to residue, I don't know, 17 or something like that. I'll hit focus, and we've got that one there. Yeah, I think that one's fine. So I'll do create, and I'll increase the strength of that one and play again. And maybe I want to have this brought over more here. And this is still kind of getting a little bit confused here. So maybe I'm going to go to structure. I'm going to create a new pose. I'll call this pose B. Stop the playback, load pose and rewind. And I'm going to create another handle at residue. Yeah, let's do a handle there. So we'll create that handle. I'll increase the strength again. Hit play. And I'll just maybe bring this up here. And maybe this handle, just bring it around this way. Something like that. So yeah, you can kind of get detailed in how you want to pose it. And you can see here that the peptide state is still trying to simulate and trying to reduce it to more of a favorable configuration of all the atoms. So hit pause again, come back to the structure and new pose, and I'll call this pose C. And load pose and rewind. Okay, so maybe I'm kind of happy with that. And I could kind of stop there, but I might want to go a little bit further. So let's look at the dynamics tab here. Dynamics is where we can add some turbulence. And so that's going to kind of shake up the structure a little bit, kind of give it some random Brownian motion so that it kind of is not quite so regular in its structure. So if I hit play, and I could start increasing this field magnitude, and you can start to see that this is all kind of starting to flex and sway. And these handles as goals are still in play. It's still kind of keeping that link there. And these handles are still allow you to influence the structure. But there's some turbulence going on. And I could increase the frequency of it to get more fine-grained turbulence. And I think I'm going to grab this handle here, kind of bring it out. Just play around with it a little bit. Okay, and then I'm going to pause that, and without loading a pose or rewinding, I'm just going to turn the magnitude down, and I'm going to play some more just so that the peptide state can resolve a little bit and get into a more favorable conformation without the turbulence kind of mixing things up. Okay, so I noticed that I was getting some bad, quite a lot of bad situation with the peptide state, and I was trying to figure out why that was. And I think what was going on, so I went down to this handle here, this handle here, and if I enable that, or if I had it enabled, this was kind of pulled out, kind of this like the square form, and I think that that was not necessarily favorable. I'm just going to stop the simulation there. This is apparently a better conformation. It's kind of straight here. And part of that might be all these prolines in here, kind of trying to force more of a bend. I'm not really sure. But yeah, you can just kind of play with it until you get something that has a good peptide state. All right, so maybe we're happy with that. Now, how do we get a surface mesh? So you might look through here looking for different meshing options, or even a backbone or something like that, and there aren't really any of those options. How do we do that? Well, what we need to do first is we need to kind of bake this into its own PDB. We need to export this, and again, that's under the structure tab. So if we go structure and then export, what we want to do is export this peptide chain into its own PDB. And so we can do that just basically clicking this export button, and we could save this as eIF4E tail, something like that. Okay, and now if we go back into the PDB import, we could actually find this file and import it. And now we have this as its own PDB. So we could turn on the backbone viz, we could turn off the atom viz, and we still have the modeler chain visible. So I might just go back to display and turn off the asset visibility. And there we go. So we've got the backbone here, but you'll notice that it's not connected to this one. And if we also did something like a surface mesh, you can see that this is going to be meshed separately from this one. Is there any way that we can get them together as a single chain? Because that's really what we want. Well, yes, there is. So I'm going to delete this and go back to my modeler chain. And again, in the export options, we can include connected chains. And so what that's going to do is it's going to include this connection and the rest of the chain that's connected to it. So it knows that this one's called chain B. This is chain B. And the first residue ID, I'm not exactly sure how that's working. When I was playing around with it a little bit, it didn't seem to make too much difference to the data that was exported, but you could kind of explore that a little bit if you want. And we could include other chains like this A chain if we wanted that as a separate chain, like not all together in a single chain, but one chain called chain A and one chain called chain B that includes this flexible tail. But I'm going to leave that off for now. All right, so we're going to export, and I'm just going to call this eIF4E as the full thing. And again, I'll hide this. And I'm going to import There we go. So now we've got the full thing with that tail all nicely connected up. If we go to ball and stick, we can see that we've got the proper connections, and to see that's alpha carbon, there's the carboxyl carbon, nitrogen, alpha carbon again. So that's all connected up in a unified chain. If we do backbone, let's go back to this one and hide it. There we go. That's a single chain. And if we do a surface, high res, there we go. There's all our full eIF4E initiation factor with that little GDP small molecule connected to it. Okay, I think I'm going to leave it there because this has already been a bit of a long tutorial, but there were some other things that I did for the illustration. I put a skeleton in the tail so that I could pose it and have it move to get the kind of motion blur that I wanted on the tail here to show that it's a flexible, disordered part of the protein. And the mRNA, I pulled that in from a PDB ID called 3MEI, and that's a regulatory motif from something mRNA. I'm not really sure exactly what this is actually about, but it's mRNA, and that's what I wanted. the primary structure, this should be correct. The secondary structure might not be super accurate, but it's a small section of it, so it shouldn't be too far off. And I just posed that so that it was connected to that existing 5' cap properly. Yeah, so I actually converted this into actual geometry. If you do want to see a tutorial on doing that, where you can actually change the ball and stick particle representation into actual geometry that you can shade differently and do different things with, please let me know in the comments. I could make a tutorial about that. Or if there's something else you want to see a tutorial about relating to molecules and Maya and things like that, please do let me know in the comments. But I hope you enjoyed this and hope it was instructive, and I look forward to seeing what you guys are making with Molecular Maya. See you next time.